The next speaker is going to talk about net zero energy institutional buildings in Singapore, air conditioning design and operation. This talk is of great interest in today's context since the idea of net zero energy building is quite challenging in any climate. It gives even more complex in an urban city in a hot humid climate with year-round air conditioning. In this talk, he discusses about key design principles of net zero energy building in the context of an institutional buildings in Singapore with a focus on the air conditioning and mechanical ventilation design and operation. Our speaker is a tenured professor and co-director in the Department of Building, National University of Singapore. His research interests include thermal comfort, ventilation, energy efficient HVAC systems and building energy analysis with about 275 publications in these fields in international journals and conferences. He has been recognized through several awards including E.K. Campbell Award of Merit, Environmental Health Award, Exceptional Service Award and Distinguished Service Award from ASHRAE and Asian Energy Award. It gives me great pleasure in welcoming Dr. Chandra Sekhar.
Good day to everyone. This is Chandra here, professor in the Department of Building at the National University of Singapore. It is my great pleasure to be part of this conference to deliver this keynote presentation titled Net Zero Energy Institutional Building in Singapore, Air Conditioning Design and Operation. I would like to extend my thanks to the organizers of this conference, Econ Best 2021. The School of Architecture and Interior Design at the SRM Institute of Science and Technology I wanted to start off with this collage of buildings and skyline from different parts of the world to just get home an important message that is related to the key subject of my presentation. Buildings, whether they are in warm climates, cold climates, hot and dry, hot and humid, whatever. They serve the purpose of providing spaces for work, recreation, residential requirements. So they need to take care of what we would call the health, comfort of the occupants. But in so doing, there is a tremendous energy implication, and that's really the message I wanted to communicate through this slide. The energy demand, the energy use intensity of buildings in different parts of the world are indeed quite a lot, and we need to be mindful of that. So if we keep that as an important criterion, and then we say that healthy and sustainable built environment really forms the backbone of urban landscape, cities and communities, there are buildings that consume energy. And then if we want to make the health, comfort, and sustainability question an important driver, we need to be looking at the notion of zero energy buildings. To be more precise, I'm going to be talking to you about the net zero energy building concept. All buildings, no matter where they are built, it would be wonderful if we can look at optimizing its performance, its energy performance, its human-centric performance without consuming any unit of energy. In other words, passive design optimization is the fundamental approach that is part and parcel of any curriculum, be it in engineering, architecture. It's well understood. How do we optimize in a passive manner? Building orientation, how the building is sited, the facade system in the building, the window wall ratio, how much glazing we provide on the surface of the building, on the facade of the building, the glazing properties. And then all of these have a direct impact on the occupants in a building. What's that? Thermal comfort, visual comfort, air quality acceptability, acoustic comfort. Can we get natural ventilation? Can we have more daylight? Can we minimize the sound that gets transmitted from the external setting into the indoor environment? Having done the passive design optimization, we could then be looking at what are the energy consuming entities in a building. And surely lighting comes in as one of the important requirements. We do need artificial lighting in certain parts of the building, certainly in the interior parts of the building where you will not be able to get much of daylight utilization, we will need artificial lighting. Now the question is to what extent we are able to blend the use of daylight together with whatever artificial lighting requirements we need. So efficient luminaires and use on demand when occupants are present, demand use of space, not just for lighting, but for air conditioning control, environmental control. When we are talking about environmental control, then the air conditioning components come into picture. And here we're talking about the plant, HVAC plant as they are referred to, chillers, boilers, accessories, air conditioning systems, fans that move the air. It could be the outdoor air for ventilation. It could be the return air from the space for cooling, or you don't need to move so much air. Let's bear this in mind. The less air we need to move, the more energy we can save. So all of these are energy consuming elements in a building. And I try to again relate to the human centricity part of it. The lighting obviously has a direct impact, again, from the context of artificial lighting. The HVAC plant or a boiler plant that stays somewhere in the basement of a building or the rooftop of a building doesn't directly impact the occupants. But then through the systems, the air conditioning systems, the air moving systems, fans and diffusers, you have several things that are right there in the occupied zone. So they do impact the occupants in a building because they realize they will be able to relate to the fact that it is these systems that are responsible for the type of environment they are exposed to. I want to bring home this point that in the process of an energy efficient design, a high performing building, the notion of minimizing demand, both from the point of view of energy consumption into the for the building, as well as demand from the use of water, demand from the use of, say, the need for other types of utilities. Waste disposal is one such utility. We need to understand how we could cut down the demand in whatever ways we can. In this context, in Singapore, we have had this notion of a green mark certification. This is managed by our Building and Construction Authority. So the green mark scheme in Singapore started in 2005. And you can see here the main focus is an environment-friendly building design to look at all aspects of sustainability, all aspects related to indoor environment, outdoor environment, minimizing waste, better resource utilization. And the key question that we always want to ask is consumption of resources, what impact does it have, both internally in the building and externally to the environment? Just a simple overview slide here to show that the notion of green mark scheme is very similar to other rating systems like the LEED and BREEAM and other similar systems. We look at the holistic approach from a sustainability perspective. And here points are recorded. And then we have the latest one that we're currently using in Singapore for non-residential buildings. And then there's one for residential buildings. And there's a whole series of different types of building applications for which there are green mark certification possible, and there are points that can be accorded. This one talks about the green mark platinum, gold plus, and gold. the points, the score, so to speak, that needs to be obtained for a building design. 70 and above is the point that one needs to have a Green Mark Platinum rating. Singapore's green journey, as I just very briefly alluded to, started back in 2005. The very first building, the National Library Board headquarters building, then an iconic building in Singapore, it still is. And it was the first building to get the Green Mark Platinum. And my colleagues and I, we had the opportunity of being engaged in the building design process through extensive simulations for natural ventilation, wind flow, energy simulation, building automation system controls, and those sort of details. Today, 2021, some 15, 16 years down the track, there's been significant progress in terms of how much of building projects, cross floor area in Singapore have met the green building standards. We have a target of 2030, 80%, meaning to say by 2030, 80% of all building projects GFA in Singapore should meet the green building standards. As of April 2019, 40% has been achieved. The challenge is always when we head towards the end, or when we progress and advance in the whole process. Existing buildings, that's where the challenge comes in. And a lot of effort is directed towards making that possible. We have, for the last couple of years, sort of a framework for the super low energy buildings. And the link that you see on the slide gets you to go and look at some of the details of what this might entail. Very broadly, there is a super low energy concept that says the best-in-class energy performing building that achieves at least a 40% energy savings based on prevailing code. The zero energy building will be the best-in-class performing building with all the energy consumption, including the plug load, supplied from renewable sources, and that is on-site renewable sources. So my talk today, when I discuss with you the case study, is about one such building. In fact, the very first building in Singapore, custom built as a zero energy building, which is our own building on our campus. It's called SDE4. I'm going to be talking about that to you shortly. It's right here. So this is a 6-storied building, the gross floor area of about 8,500 square meters, and it has a whole suite of functional areas, design studios, hot desking areas, research centers, laboratories, workshops, libraries, seminar rooms, and the like. I will take a couple of minutes on this slide to just take you down, or walk you through the concept or the framework or the approach, if you like, that we adopted in getting towards a net zero energy building. So if we see here right at the top, we have a reference building which consumes about 1947 megawatt hour per annum. And then optimizing the envelope brings it down to 1600 thereabouts. That's the optimum design in terms of the envelope. Then we have a high efficient air conditioning system, brings it down to the 1200 mark. Hybrid system, 820 megawatt hour per annum. I will discuss with you what the hybrid system is about. And then the optimum design, after a few iterations, the final one was about 497 to be precise, megawatt hour per annum. The 497 megawatt hour per annum energy demand is produced by on-site PV production using solar panels. That's about 510 megawatt hour per annum. So you can keep the figure of 500 in mind, and these solar panels details are mentioned here, about 1,200 panels, 510 megawatt hour per annum of energy generated, 424 installed capacity. Let me proceed further. This building obtained the Green Mark award, the BCA award rather, in 2018, Green Mark Platinum. And some of the details in terms of the features of this building are sort of presented on this slide. The building was completed and launched in 2019, early 2019. And you can also see here this whole concept of a well and green precinct that kind of very clearly and nicely integrates human-centric design with a sustainable environment. That's how the building looks like. It's a very nice building. We go there for several purposes: classrooms, meetings, labs, research center activities. It's a very nice building to be in, and it gives a very pleasant, wonderful experience. The subject of my presentation here today is on the concept of hybrid air conditioning. I'll spend a bit more time to talk about what this concept is and how that has contributed towards the net zero energy building for SD4 narrative. So the idea is to reduce the cooling demand by increasing the space temperature and then using air movement to provide better comfort and perception and the like. Conventional system, 24 degrees Celsius, comfort and air quality probably pretty good. Energy is high, as we all appreciate it. The same conventional system, if you increase the temperature to 27 degrees, we notice that thermal comfort and air quality could be a problem. With the dedicated outdoor air system, that is the concept, that is part of the concept in the hybrid air conditioning, we provide the space at a temperature of 27 degrees Celsius. Now that's not going to be very cool and comfortable by itself, but if we create increased air movement through fans, it becomes very well as an environment, becomes a pleasant, acceptable, more than an acceptable environment. So the concept of a DOAS ceiling fan system is to keep the space at a warmer temperature, 27 degrees Celsius, accompanied by increased air movement. One of the things that we need to bear in mind is when you come from an external environment that's hot and humid like we experience in Singapore, immediately into the environment, you may need to have an increased cooling to begin with. So you may need this fan to be at a much higher speed perhaps, so maybe the space temperature is slightly cooler you would have preferred. So there is this transient state, as you would call it, right? But after a while, and it's not too long, probably about 10 minutes, thereabouts, it gets in fact, it is pretty good neutral within a few minutes of entering, but after some time, maybe about 10 minutes, 12 minutes, 15 minutes, it depends on each individual. The steady state phase is a continuous experience and exposure of a very pleasant environment. And this is being achieved at 27 degrees Celsius. So I'm going to share with you two sets of studies. One is the mock-up room studies. It's part of my former PhD students' work. And now Dr. Kuriaki Mihara, this is his work. And he did this study in a simulated mock-up room in an existing part of our building. And then he set up instruments to measure all the temperature, airspeed, humidity, environmental parameters, and then he arranged the layout in such a way that subjects could walk in and be seated in these chairs, about 8 of them, as you can see here, and they can respond to the environmental conditions. We follow a fairly comprehensive questionnaire responses that we solicit from the subjects participating. Some more details about the mock-up chamber room. This is the ceiling fan, and these are the layout arrangements. Some details about the room dimensions, etc., are given here. And we note here that the sort of system that we use here for the DOAS and CF is very similar to what would then eventually be part of the new SDE4, because this experiment was done in 2017, 18, to late 2017, early 2018. Several instruments were used to measure temperature, humidity, radiant temperature, an anemometer for the airspeed. We have a thermal mannequin, a breathing thermal mannequin that allows us to do um, detailed measurement related to the ventilation performance. We use tracer gas techniques to compute air change rate and those sort of details. Very, very quickly, overview slides to talk about what the results told us. Air movement. We see here when the temperature is 24 degrees Celsius, uh, when there's no air movement at all, that's the ideal condition. So people just like the 24 degrees temperature. But when you increase the speed, by any chance, if you want to have some air movement, somebody might need it, not all, then we find that there are a lot of people who do say that they would not want the air movement. In other words, 24 degrees, no air movement just works. That is just the similar environment that we experience in typical air-conditioned buildings. Now, 27 degrees Celsius, when we raise the temperature, when we have fans running at about 1 meter per second, that's this middle one, notice hardly anyone wants to change the setting. They like it. Thermal comfort, right? We find that 27 degrees and 1 meter per second, it's as comfortable, in fact, most comfortable setting compared to even the 24 degrees. Indoor air quality acceptability. Across the board in all the experimental conditions, we noticed that it was found to be very good for the simple reason our study here in this walk-up chamber as well, we use 100% outside air. There's no recirculation. So the idea of providing 100% outside air from a ventilation perspective, from an exposure control perspective is always a very good idea. And I think that's what is contributing to air quality being very good. In fact, much, much better than any other typical air-conditioned building at all conditions. Let me now go to the field studies in SDE4, Zero Energy Building. This was done after the building was commissioned. As I say, it was launched in early 2019. In the first half of 2019 were the experiments conducted. You can notice here that there are two parts. The red block here, that's the design studio, which has the hybrid concept, DOAS and ceiling fan combined. Then there's a conventional computer lab setting where we have the conventional FCU system, the conventional air conditioning unit. So we are comparing in the field study what's happening in the typical conventional air conditioning system, served space that's 24 degrees, with this design studio that is served with hybrid system and ceiling fan concept, 27 degrees and elevated airspeed. Some details. There are two types of classes, two different types of studios. S2, S3, and S4 is for year 1 to 3. That's got a larger area, 457 square meters, and the year 4 design studio is here. So S1 is for year 4, S2, 3, and 4 is for years 1 to 3. A total of 235 subjects were involved in this study, 61 male and 174 female students. What did we measure in terms of the environmental conditions? Typically in the studio space, about 26.5 to 27 degrees Celsius. Humidity was about 58, 60% RH. And we noticed that in the computer lab, it was 24 degrees and 55%. The humidity is about similar in both settings, the FCU space and the DOAS and CS space. So point to be noted here is the design studio, the environmental conditions are measured at much, much warmer conditions, 27 degrees sort of a temperature. Now, what did the subjects tell us? And this is the most important part of our findings. Operative temperature that we obtain here from thermal sensation when we compare it, okay, we find that 24 degrees, that's the operative temperature because we have considered in plotting this figure, the air temperature and the radiant temperature. And here we find for the DOAS ceiling fan, which is around 27 degrees Celsius. Just to bear in mind, if you had taken note of the previous slide when I showed the measurements, there wasn't much of an impact of the facade in terms of the radiant heat gain. They were not too different from the air temperature. So we can more or less say that this is most dominated by the air temperature. What about this figure here? In terms of the statistical significance, we find that the DOA CF is better compared to the FCU system in the computer lab. Now, we might argue that even the FCU is good enough, and it obviously has to be good enough. It's conventional air conditioning system design. What's interesting here is that the dual CF does slightly better in terms of how people have perceived the thermal sensation to be on the scale, as you can see here. And then there is a statistical significance. Thermal preference, again, we notice between the DOA CF and the FCU, DOA CF performs better. That's a thermal preference. Thermal comfort acceptability, again, we find that the DOA CF is that much better. Again, it's statistically significant compared to the FCU surge space. Thermal acceptability as well, similar context and similar information that we find. So all said and done, if we look at the slide, we can very easily conclude, very safely conclude, that the DOA CF is able to maintain better comfort, better thermal acceptability. The thermal preference is as good, or if not even better, and the thermal sensation of the subjects as expressed through the responses. Everything points to the fact that 27 degrees and the airspeed, I would say it's about 1 meter per second. The subjects find it comfortable, it's to their liking, and they are happy. Air movement preference at 60 minutes after the start of the lecture in the studio in the computer lab. Again, we find that the DOA CF, there aren't too many people they are asking for anything different. In other words, they are quite satisfied with the air movement that they get. And in this particular set of studies, the students could choose where they want to sit. So they were given a space or given a zone in the S1, S2, S3, and S4 part of the design studio. As you would well appreciate that there could be some local variations in the airspace. The students are given a choice to sit where they want to. They chose where they wanted to sit in terms of I want slightly more air movement, slightly less. When they were all settled at 60 minutes after the start, you find that they were happy. They weren't asking for anything different. Air movement acceptability, you notice here that with the DOA CF, there is a slightly less percentage of people who are indicating that they weren't acceptable. And all this information is statistically significant. You can see here P less than 0.05, and here it's P less than 0.01. The indoor air quality acceptability and dry eye discomfort at 60 minutes after the start. Again, we find the DOA CF and the FCU, they are both equally good, and I've already given you the reason why that is the case. In both situations, we are indeed ensuring that the right amount of ventilation. In fact, the DOA CF is even better because it's 100% outside air. In FCU, there is an element of recirculation that is involved, but then it's providing the right amount or required amount of ventilation. Again, this is a kind of symptom-related analysis based on how we collect a questionnaire from the responses through the questionnaire from the subjects. And again, we find that dry eye discomfort acceptability, there isn't too much of a difference between the two. So environmental conditions wise, the DOA CF system does as good a job as the conventionally designed FCU system does. I'm now going to talk a little bit about the energy side of the analysis. We find that for these three spaces, that is the design studio year 1 to 3, that is S2, 3, and 4, and then the computer lab, design studio year 4 is S1, and then the computer lab is by itself, a conventionally designed space. So the yellow is what you require based on standards and codes. The average outdoor airflow rate supplied as measured is over here. And you can see here, in terms of what is to be supplied, if you base it on design occupancy, you find that the number is the one that you see in the red. And then when you base on the actual occupancy, we provide a lot more. So that's basically what we are looking at. So the reason we are able to provide more outdoor air as ventilation in the case of the design studio is simply the fact that there is no recirculation. Since we're maintaining at a warmer temperature, the energy consequence or energy implication of that is hardly anything that we need to be too concerned with. In fact, this just demonstrates that there is a potential to use some level of demand ventilation and probably have an even significant impact in terms of the energy conservation. The reason I'm showing you these numbers is to say, what do these numbers mean in terms of the absolute percentage energy savings? To do that, from the measured data, we need to be able to compute, we need to be able to estimate, let's say, the cooling load demand in these spaces. Here it is for the average normalized cooling coil loads, measure heading towards energy conservation or energy efficiency sort of information. So the studio year 1 to 3, which is on the DOA CF concept, is about 30% reduction compared to the computer lab, because that is our reference point. And the year 4 is about 38.6. The computer lab reference point, the loads are high, or the cooling load on the coil or the demand is high for a variety of reasons. Cooling coil is a place where the cooling needs to be done. The reason is you're maintaining it at a lower temperature in the space, 24 degrees, as opposed to 27 here. And then the other loads in the computer lab related to the plug loads are high because it's a computer lab. There's going to have computers installed, and that's going to cause an increase in the loading for computer lab. So we kind of take all of that into consideration and then determine what the energy savings is. And here, the same outdoor airflow supply that I showed you in the previous couple of slides before, and this is for the period of 1st February to 31st March, during which time the data were closely monitored for the purpose of computing the energy analysis. So design maximum is in blue. That's what the systems are designed for. The average outdoor airflow rate is kind of close to design maximum, if you like. And the computer lab is slightly lower. It's just the way the systems operated at the time. And here we find that the average outdoor airflow rate supplied, they are comparable for all 3 scenarios. That means all 3 zones. This is S2, 3, and 4. This is year 4 is S1. You remember the design studio has got S1, S2, S3, and S4. And the computer lab is by itself. So this is the average outdoor airflow rate supplied. So based on these numbers measured as collected from the system, we compute that the energy savings is 26% for the year 1 to 3 studio and almost 30% for the year 4. So there is, this is the mean daily energy consumption per floor area. So it's watt-hour per meter square. That's what we are computing. So you notice that the DOA CF system is able to provide comfortable, satisfactory environment at 27 degrees with elevated airspeed of the order of magnitude about 1 meter per second, thereabouts. Some part of the space may be slightly lower, some may be slightly higher. And if you give the students a choice, that's what happened in this field study. They are all pretty much satisfied and express comfort with the environment. The building has been now in operation for slightly more than 2 years. And over the years, couple of years, it has received several accolades. It received in October 2019 the well certified gold, and is the first building in the world to receive, first university building in the world to receive that, and also the first building in Singapore to achieve that prestigious well certification. Towards the end of last year, in November 2020, this building, SD4, is the first in Southeast Asia to achieve the ILFI Zero Energy certification. So just as a quick summary of what I've been talking to you about, the concept of net zero energy building, the drivers for such a design, and the approach or the mechanism that will lead us towards that, optimizing the passive design as much as possible, and then to minimize the demand for any active energy requirement. So that exercise right in the early design stage is extremely crucial, so that we are able to determine what is that energy that we really need to produce on site. And if that is done, producing the energy, in our case, it's through photovoltaics, using solar panels on the roof of the building, on-site production, we are able to balance the energy demand with the energy production. And the example of the SD4 is able to show us that it is possible to do such designs in a hot and humid climate. We are excited about what the results have been telling us so far, and we hope to be able to continue monitoring the results and to be able to fine-tune and refine some of the set points and the operational characteristics, so that we continue to sustain the high-performing building that SD4 is. With that, I would like to thank you for your attention. Thank you very much.
Thank you, Professor Chandra for your enlightening presentation on net zero energy institutional building. I'm sure that the students and the research scholars and professionals have found it to be a very informative presentation.
Welcome to the course Color Psychology. The first module, the background of color, will give you an overview of multiple perceptions in color. We will learn about the scientific background.
I have scientific proof that white light is composed of 7-component colors.
Understand basics of color theory. Take inspirations from colors in nature.
Context matters, you know.
Teleport to different time zones to get historical perspectives of color.
Is Greek architecture devoid of colour? Isn't it completely white?
And finally, dig deep into the human mind to get psychological perspectives of color. We will then go on to explore color in various spatial typologies of architecture and interiors. A transition from theory to practice would happen in the last module on practice and application of color. The journey would be immersive with fun quizzes and activities along the way. Join us in this colorful, fun-filled journey.
Hey!